Hello everyone. So today we shall be covering the Otto cycle. Here's a PV diagram for the Otto cycle. So before we go into the specifics of the different types of steps you have in it and the equations to define it, we'll talk about where the Otto cycle is used. Well, an Otto cycle is a closed system cycle, which means the mass in is the same as the mass out, like not just the content or the amount of mass there, the physical contents is the same. As a closed system, there is no mass changing across the boundaries of your system. So as a result, we're not going to be dealing with flow rates, we're just going to be dealing with the amount of mass that is present. Often these are used in engine cycles or that's when it's used in engine cycles. Like we'll be covering the diesel cycle in our next video. The diesel cycle is a closed system cycle, and I'll go into more explanation about that in its own video. But this is a closed system. So let's now go over the steps. So 1 to 2 is isentropic compression. From bottom dead center, so bottom dead center to top dead center. Now, what is bottom dead center and what is top dead center? Well, bottom's dead center is simply the farthest down the piston will go. Top dead center is the highest the piston will go. So this point here at 1 here is the bottom dead center point. Here at 2 is the top dead center point. So 2 to 3 is isochloric heating. Isochloric means constant volume. So this is where the heat is being pumped into the system. Heating. 3 to 4 is isentropic expansion. So you're going from bottom dead center, or from top dead center back to bottom dead center. And 4 to 1 is isochloric heat rejection. So let's discuss this in regards to an engine. So here from step 1 to step 2, fuel is entered the compression, enter the system, and I am now compressing it upwards. Then 2 to 3, isochloric heating, piston is at the top, hit the igniter, the fuel is heated up or the air is heated up, and then 3 to 4, isentropic expansion, the pressure is now pushing the piston down again, and then 4 to 1, it's at the bottom, the exhaust is being released, and more fuel is being dragged in. So, Otto cycle. One thing prior to learning for the Otto cycle is, since it's an engine cycle, you're going to be dealing with air, because in a lot of engines, the fuel to air ratio is very drastic. You're going to have substantially more air in there than you're going to have actual fuel. As a result, when you're doing an Otto cycle, you're going to be dealing with air. And no, that's it. You're just going to be dealing with air. So let's do the first law analysis of this. Remember, because this is a closed system, we're dealing with delta U is equal to Q minus W. So 1 to 2, isentropic compression. Remember, isentropic means adiabatic and reversible, so therefore heat is 0. So U2 minus U1 is equal to the negative work divided by the mass present. So then the work of the system is equal to U1 minus U2. All right. So then 2 to 3, isochloric heating. Well, if you recall, work is equal to the integral of the pressure with respect to volume. If there's no change in volume, it's 0. So you get delta U is equal to Q over M. You get U U3 minus U2 is equal to Q over M. So now we're right here. So now we're going to adiabatic expansion. Adiabatic expansion. Well, adiabatic, remember again, Q is equal to 0. So you're going to get same system up here. You're going to get the work divided by the mass is equal to U3 minus U4. Alright. 421, we're going to do isochloric heat rejection. So U1 minus U4 is equal to Q over M. Alright, so here is the first law applied to each step of our process, and then for the efficiency is equal to the work net divided by Q in. If you recall, the work net is going to be the work you get out of it minus the work you put into it. So it's going to be U3 minus U4 is the work you put in, because that's the adiabatic expansion, minus the work you got through compression, which was U1 minus U2, all over the heat you put in during the first isochloric section, 2 to 3. So Q23, which is going to be U3 minus U2. Now, one of the other things you're going to have with an Otto cycle is a compression ratio. You're going to be how much you went from bottom dead center to top dead center. So it's going to be the compression ratio. Where R is equal to V1 over V2, because recall, since V4 and V1 are the same volume and V3 and V2 are the same volume, you're going to have your top dead center here. This is the lowest volume you're going to have. This is the highest volume you're going to have. Now, when do you use compression ratio? You use compression ratio when you're operating under cold air standard cycle. Now, what is cold air standard? What does that mean? Well, that just means you're treating air as an ideal gas. Now, this is great because with you're treating air as an ideal gas, over the centuries, engineers have tabulated all these values for air at specific temperatures and pressures, and you get reduced pressure and reduced volumes, and you can get these volumetric ratios. Well, what is reduced pressure? Well, and reduced volume? Well, V sub R1 and V R2, which is the reduced volume for state point 1, state point 2, is equal to the volume at 1 and the volume at 2. This VR is just a tabulated value to help organize the data. So let's now move on. So why is this important to us? Well, at cold air standard, we might not know the temperatures at state point 4, state point 3, or state point 2, and we need to find out what they are. Well, that's where the compression ratio can come in handy. So at cold air standard, we get T2 over T1 is equal to V1 over V2 to the K minus 1, which means T2 over T1 is equal to the compression ratio to K minus 1. Well, what about T4 and T3? Well, T4 and T3, you might notice, let's just switch it up the two, is going to be 1, the ratio between them is 1 over K minus 1. You might notice that. Oh, but John, if you just did T1 divided by T2, you get 1 over R to the K minus 1. It's the same ratio. Yes, it is. So you can use that type of system because you're going from final to initial or initial to final. For cold air standard, for the adiabatic processes here, you can use this formula. For an Otto cycle. So let's deal with, well, now what's the efficiency of the system? So we're going to say at cold air standard at constant volume, your efficiency equation becomes N is equal to 1 minus your specific heat at constant volume times T4 minus T1 over the specific heat at T3 minus T2. So this is our efficiency equation from this. So then we do simplify this more. Control volumes cancel out. We get divide by T1 is equal to 1 minus T1 times T4 over T1 minus 1. Let's put a parenthesis around here too. Factor out T2. You get T3 over T2 minus 1. And now you're going to wonder why I brought up that ratio sooner. Well, this is why. Because if you notice this, T4 over T3 is equal to T1 over T2. Therefore, T4 over T1 is equal to T3 over T2. Therefore, these cancel out. And you get your efficiency is equal to 1 minus T1 over T2, which is equal to 1 minus 1 over R to the K minus 1, where, remember, under cold air standard conditions, K is equal to 1.4 for air. And what is K? Well, K is the ratios of specific heats. K is constant specific heat under constant pressure divided by the specific heat under constant volume. Well, by looking at this equation, you can see that if my compression ratio increases, my denominator here is going to increase, reducing this fraction and increasing my efficiency, which means that the more air you're able to compress, or the more volume you're able to compress, the better your engine will perform. So this is the math behind an Otto cycle, and I will set up and we shall do an example problem shortly. Hello everyone, so here's the problem that we shall be doing today. We have an Otto cycle here. We know the values of state point 1. You might have noticed we're doing imperial because you know what? Why not? This is America. Gonna do imperial. So T1 is equal to 540 degrees Rankine. Pressure 1 is at 1 atmosphere. V1 is at 0.02 feet cubed. The system has a compression ratio of 8. And we know we have a maximum temperature of 360 degrees Rankine. We want to find the temperature and pressure at each state point, which means 1, 2, 3, and 4. And we want to find the mean effective pressure of the system. And we want to find the thermal efficiency of the cycle. Well, guess what? State point 1 is right there. We're given the temperature, we're given the pressure. So that was easy. State point 1. Temperature is 540 degrees Rankine. Pressure is 1 atmosphere. Cool. So now let's find the other sections of it. Oh, but wait here, we're given maximum temperature too. Well, the maximum temperature for an Otto cycle is of course going to occur when you're done adding heat to the system, which is going to be at state point 3. So let's find my mouse. State point 3. And you may have noticed these charts. Well, these are the charts I was telling you about earlier where the values are tabulated. You have the temperature in Rankine, as you can see here, the enthalpy and internal energy in BTU per pounds, the entropy, which we won't be really dealing with, and then we have the reduced pressure of the system and the reduced volume, specific volume of the system. Well, state point 3, I'm given a temperature of T3 is equal to what? 3600 Rankine, right? 3600 Rankine. 3600 degrees Rankine. Well, go here. I don't know my pressure because I'm given PR, but I know VR. And why am I using VR? Well, recall, this says, I didn't write it here. Well, this system is operating under the cold air standard. I wrote it, then erased it when I was organizing stuff. That's my bad, but this system is operating under cold air standard. So V sub r is going to be 0.6449. And state point 1, let's go to 540 degrees. V sub r is r sub 1 is equal to 144.32. Alright, so now let's find the values at each state point. Well, let's just go in order. Let's go to state point 2. If you recall, I am given the compression ratio here of 8, and that R is equal to V1 over V2, which is VR1 over VR2, which is equal to R. So at state point 2, VR1 over VR2 equal to R. VR2 is equal to VR1 over R. That gets me 144.32 over 8, which is equal to 18.04. So let's go here, look for 18.04, and it's right about here, between 1200 degrees and 1240 degrees. Well, I'm not going to interpolate. If you want to, you can. We covered interpolation before, and this is to save time. It's been done, and so we get that T2 is equal to 12 degrees Rankine. And then U2 is 211.3 BTU per pound. Alright, so now let's do everything else. Well, we need the pressure after state point 2. Well, luckily for us, this is an ideal gas going under an isochloric process. Therefore, if PV equals nRT, we can just do V1 is equal to T1 over P1. Well, not really 1. This is going to be 2. So, draw, eraser. Oh, didn't mean to do that. And R. So V2 is equal to T2 over P2. And then, no, well, if we did it for 1, 2, that'd be P1 V1 equals nRT1, or V1 is equal to T1 over P1. So, well, remember, since this is a closed system, R is a constant, N is the amount of moles that are there, therefore, these will be the same. Therefore, if I can find my mouse, I'm going to increase this size because this is annoying me. P1 V1 over T1 is equal to P2 V2 over T2. This was not necessary. Solve for V2. Wait. No, I'm not solving for V2. I'm trying to solve for P2. So, that's my bad. P2 is equal to P1 V1 T2 over T1 V2. Well, what's V1 over V2? Well, that's the compression ratio. So this becomes 1 atmosphere times the compression ratio 8 times T2 divided by T1, which is 12 over 540 degrees Rankine, and you get 17.96 atmospheres. Therefore, now I know what P2 is, and I know what T2 is. State point 2 is done. State point 3, however, is not. So, state point 3. Well, recall that 2 and 3 have the same volume, therefore P2 over T2 is going to equal P3 over T3. So P3 is equal to P2 T3 over T2 equal to 17.96 atmospheres. times 3600 degrees Rankine over 1212 degrees Rankine, and you're going to get 53.3 atmospheres. All right, so we already know the temperature is state point 3, so now we can move on. State point 4. All right, so we have VR4 over VR3 is going to be equal to V4 over V3, which is equal to V1 over V2, which is equal to 8. So VR4 is equal to 8 VR3, to 8 times the value I got above from the table, 0.6449, equal to 5.16. Go up to the chart, look for 5.16. That's interpolation. Not going to do that. So interpolate, blah, blah, blah. You get T4 is equal to 1878 degrees Rankine. U4 is equal to 342 BTU per pound. So that's fine. The pressure is state 4 using ideal gas equation. Remember, V1 equals V4, so P1 over T1 is equal to P4 over T4. P4 is equal to T4 over T1 times P1 is equal to 1 atmosphere times 1878 over 540 equals to 3.48 atmospheres. So now we want to find the thermal efficiency. Thermal efficiency. Well, this is cold air standard, so we can use the equation N is equal to 1 minus 1 over R to the K minus 1. Well, that's 1 minus 1 over 8 to the 1.4 minus 1. 1 minus 1 over 8 to the 0.4. Now, what is that, you might ask? Well, I will tell you in 1 second as soon as I get my calculator out and can do the value of it. Let's go here. 8 to the power of 0.4 is 2.3. So that's equal to 1 minus 1 over 2.3. That is equal to 0.565. So the efficiency of the cycle of cold air standard is 56.5% efficient. Alright, so let's now calculate the mean effective pressure of this cycle. I appear to be at the bottom of my page. That's what happens when you write big. Let's add some space. Alright, so now the mean effective pressure. Alright, so we know the work of the cycle is going to equal to M times U3 minus U4 minus U2 minus U1. Alright, so we need to know first off the mass of the air, so mass is equal to rho V over the gas constant divided by the molar mass of air times the temperature. We're just going to use, we can use any state point, it doesn't really matter. We're going to use state point 1. So the pressure for 1 atmosphere is 14.696 pounds per feet squared times the, going to convert that to, no, I'm sorry, pounds per inch squared. That's my bad. Pounds per inch squared. Convert that to feet squared times the volume, which is 0.02 feet cubed, divided by the universal gas constant in imperial, which is 1545 feet times pound forces, all over, molar mass of air, 28.97 pounds per, times degrees Rankine. Pounds per foot. This entire unit is just combined. Dimensional analysis times 540 degrees Rankine. This is not the unit for the universal gas constant. This is not the unit for the molar mass of the air. Just dimensional analysis. Everything was put together. So we get this all is equal to 1.47 times 10 to the negative 3 pounds. All right. So put that into the work of the cycle. Just plug in that and the U2, U1, and U3, 4 we find here from this table into this equation here. You will get the work of your cycle is 0.382 BTU. So, if you remember, mean effective pressure is equal to the work of the cycle divided by the difference in volume between V1 and V2. Well, I need to determine what the difference in volume between V1 and V2 is. Well, V1 over V2 is equal to R, so V2 is equal to V1 over R. So, work of the cycle of V1 times 1 minus V2 over R is equal to work of the cycle times V1 times 1 minus 1 over R. Plug in 0.382 BTU, 0.02 feet cubed, 1 minus 1 over 8. You get the mean effective pressure as 118 pound forces per inch squared, which is equal to, this should have been pound force up here, which is equal to 8.03 atmospheres. So, there we go. Using cold air standard cycle, we have the state points, we have the formula we were given. We were able to use these tables and the compression ratio to determine the state points, values of every single state point, the pressure, temperature, energy, that type of stuff, internal energy. And then we combined it all. We can use, this was cold air standard, we can use compression ratio to determine the efficiency, which we did. And then we found the mean effective pressure finding the work of the entire cycle, dividing it by the change in volume. And there we go. Thank you much for joining me tonight. Have a wonderful night.